So thank you for inviting me. I'm going to be talking about harnessing opportunistic data and intuition that we may have about the way that the world behaves in order to enable autonomous buildings. Autonomous buildings being a large part of the demand, electrical demand. So let me start by introducing you to Joe. Joe is, let's say, a facility manager in a commercial building, and sometimes he's interested in existential questions, especially given the title of my talk. Will autonomous buildings be a thing, and will they take over my job? Sometimes he is interested in much more mundane questions, like how much longer until this pump dies? And the theme of the talk is whether having more information, either opportunistically obtained or not, does it provide better answers to questions like this that Joe may need for his job. And so how Joe would go about this, generally speaking, is he says, well, I kind of know this. If you give me some manuals and specifications for the pump and I send somebody to do visual inspection, I can tell you that it's about 2 years that it has left. Or if Joe's sophisticated, he may tell you about 2 years with some error, margin of error. But if you give Joe additional information, more data, in the form of opportunistic data, let's say that you have IoT sensors deployed, or you happen to have a camera deployed nearby, or some audio sensor, Joe doesn't necessarily know how to incorporate that data into his model, this function f, to come up with a better answer. Right? If you're a machine, though, and your task is to solve this as an inference problem, then you're only seeing observations, and then you have some kind of latent variable that you would like to get access to. In machine learning parlance, this would be basically a supervised learning problem. And Joe's function is a very specific kind of function, where perhaps he's saying pump life is inversely proportional to hours of operation. So what I'd like to do is to draw an analogy between, how we as people working in the machine learning applied area think about this problem and what kind of solutions we can get. So either if we treat this as a regression or a classification problem, at the end of the day, what we're saying is we have some function that we can parameterize and learn its parameters from data. And an interesting way to think about this is not an idea that is original to me. I will attribute that to Andrej Karpathy. You can think of all the possible functions in order of their complexity in this circle here. And Joe's function is somewhere in the middle. It's a function that if you give it data, it doesn't give very different answers. So its bias is high and its variance is low. But because we have other functions to work with, we can do better than Joe. If you apply any of the traditional machine learning methods, you may be covering a slightly larger portion of that circle. And the more sophisticated ones that exist right now have a very low bias, assume very little about the data, but have very high variance, right? And so the point here is that even though you can do better than Joe, and a footnote here, it would be convenient to define these functions in a way that is smooth and differentiable for the specific purposes of this talk. Even though that you can define them, this space of possible functions is huge and gnarly. And the silver lining on that is that we, as sort of engineers or domain experts, actually have some kind of map or compass to allow us to navigate this space more effectively. So we can define boundaries on the kinds of functions that we can apply. And this is where the physics intuition in my title comes in, right? So all of our physics intuition knowledge can actually constrain this space and help machines navigate it much more easily. It may still lead to computationally intractable formulations. And if we get to the second part of my talk, I don't know how much time I'll have to say everything I want to say, then I'll give you an example of where that actually comes up. But still, helping to redefine this space of possible functions is a very good thing to have. So in the rest of the talk is spend most of my time, maybe all of the time for the remaining few minutes, on giving you one case study about learning to control heating, ventilation, and air conditioning systems, which happen to be one of the largest sources for the electrical demand of buildings. and also one of the largest sources of energy consumption in the US. So I'll focus on that with the theme of opportunistic data and physics intuition. And then if we have time, I'll move on to another topic that I care dearly about, energy disaggregation, understanding how to decompose observations of the total electrical consumption in a building into the individual constituents and how much they consume. Okay. I attribute these two problems primarily to two different students that I have had the pleasure to work with. So I'm going to be using their slides and their contributions throughout the rest of the talk. So Bing-Ching for learning to control HVAC and Henning for the energy disaggregation. So imagine that Joe asks, hey Siri, can you lower my energy bill? Right. This question, even though it seems science fiction at first, we do have ideas for how to start solving this. And the two clear paradigms that exist in literature are either you treat this as a model predictive control problem or you treat this as a reinforcement learning problem. On the model predictive control side, one of the downsides is that each one of the buildings that you want to control would require a model. And the more accurate your model, the better, but it's very costly to do that, to create those models. And on the reinforcement learning side, typically, even though these solutions have become a lot better in the past few years, they require a lot of training time or exploration time for them to be effective. And so the student that I have, Bing-Ching, asked the question, what is a practical and scalable solution for doing this building control? And the easy answer is that if you look at the literature, a lot of the reports out there actually required a whole lot of time. So this is y-axis is time, training time for achieving same level of control as the existing controller, and then publication years on the x-axis. And that y-axis is in years. So for example, you can see that all of them take no less than a year of training. And some of them take up to 47 years of training. When we introduced a solution last year, we actually created the first solution that was able to do the same kind of task in a few weeks of training. And how do we do that? Well, you can guess by just the title of the talk. We did away with a simulation environment. We did not require the reinforcement learning agent to train with simulation environment. Instead, we used the historical data to pre-train the agent. But when we were working with the agent in the real world, we achieved this with a second trick. So the first trick is imitation learning, so learning to imitate the historical data as controller. But then the second trick, and it's the heavier trick of the two, is that we can now embed our intuition about how the building behaves into the policy that the agent is actually optimizing over. And we do this with the help of a group of people here at CMU that created a differentiable MPC policy. I saw that in the participants, there's at least one of these authors in the group here. And this is a game changer. So now we can actually not have to decide between using MPC or using reinforcement learning. We can combine the two and have a differentiable layer that includes the model of the dynamics and an optimizer and solves for it. I'm going to try to be quick so that I can get the story out and not focus too much on the details, but I'm happy to provide additional answers after we're done. The idea is that in the traditional way of thinking about this, the modern reinforcement learning literature would have a policy that is basically just a neural network parameterized by its weights, but the network is actually pretty opaque. We don't enforce anything specific on what the network is learning about the policy. In our case, and obviously you can train this using some kind of a policy gradient algorithm. But in our case, we don't use just a generic policy. We use this differentiable MPC policy, which contains information about the actual building dynamics. In this case, they are assumed to be locally linear, and it can also optimize this model using an MPC optimizer. So because of that, we can achieve better performance. I'll just jump in to show you exactly how much better. So in that same 47-year case that was published a couple of years ago, we took the same environment, which is a simulation environment. And what this environment allows you to do is to control the supply water temperature for a system that is basically radiating heat across different sections of the building. It's called the Mullion system. And so we control the supply water temperature set point, and with that control the amount of heat exchange. And the original controller in this space did something like this. So what I'm showing here is in the top the zone temperature of the space over the course of about 5 days, and then the supply water temperature on the bottom, which is the thing that we're actually controlling. I'm also plotting here in dashed black lines the occupancy on both of these, which as you can see, it's assumed to be very regular, as well as a set point in dashed red. So this is the supposed set point. And in the historical data that you can see here, the controller is doing a relatively good job of keeping the temperature close to the set point. It doesn't really reach the set point. And our controller also can imitate this fairly well. But when we deploy this in an actual online setting where it's not trying to imitate the previous controller, then it outperforms the existing controller. And what you can see here in the blue line is a comparison. So compare blue against black. Black is the existing controller, blue is our new controller. Yes, it can imitate fairly well, but one thing that you can also notice is that it's learning to pre-cool. So right here, for example, actually that's preheat, to preheat the building. And also it's learning that if occupancy it's going to go down soon enough, then I should also stop heating. So it's learning to preheat, and that is a game changer, because the other controller was just static and didn't have this kind of information. And it learned all of this, again, by using opportunistic data, the data that was there, and also some physics intuition to make it more efficient. This is in the course of just 4 days. It's already learning all of that. Ultimately, this achieved in simulation about a 20% energy savings compared to the existing controller, or a 6% compared to the controller that was published that took 47 years. We have results also for a real life testbed that I don't have time to talk about here. And then additional results on additional testbeds that I'm just going to point you guys to the paper that have this. Some of the limitations, of course, of this work is that we're assuming predictive information of occupancy is available. We're also assuming that thermodynamics can be locally linearized, which in some sense they can, but not everywhere. And we've only validated this in about 2 systems now with this new paper on a couple more simulation environments. But it's a topic of interest and in opening up a new way of thinking about control. I don't think that I'll have time to talk about the case study number 2, but I'll just give you a teaser, right? The teaser is there's a lot of information in the electrical consumption that the whole building is measuring. And if we know how to apply the domain knowledge or the physics intuition about what this actually says and what it means, we can create models that are efficient at extracting the individual appliance level consumption from those aggregate measurements. It does lead to computationally intractable solutions that need to be approximated. But for that, I'll just lead you to papers that I have here. Because this is going to be recorded, you can just stop and pause this and look at the papers or ask me questions if you have any. Okay, so in conclusion, there's ample data out there that we can opportunistically harness, but it's only useful when you combine it with domain knowledge of the systems that we're studying. But for this to be true, I think in general, future looking, we need more advances in these sort of implicit models that can learn from data, whereby implicit, I mean that we say what we want the model to do, but we don't necessarily create the mapping from X to Y as we usually do in practice. Okay, So that was a lot to pack. I'm going to stop here and let you guys ask me questions.
Mario, that was outstanding. And I see some questions coming into the Q&A. So I'll just kind of tee one up that I was kind of having along with one that was asked in the Q&A. And that is, just to clarify, for the application with the temperature control in the building, first of all, was it just being simulated, or were you actually running the temperature in the building? Because that was not 100% clear. And the other question that I had was, what exactly went into the into the optimization? I mean, my sense is you're using the historical data to kind of understand the relationship between the set point and the temperature of the water going in and the temperature that was actually in the building. But how did you parameterize the goal? Was it just, I want to have this temperature and there's some penalty if I don't hit it or if I overshoot it, or how did you parameterize it? So those two questions.
Okay, so to answer the first one, I only focused my attention on the simulated results that we had, which means that all of these experiments that I showed and the results are based on a simulation, and we were interacting with, the agent was interacting with the simulation. But we did, and I mentioned that very briefly, we did do an experiment in a conference room where we took 4 weeks of a conference room and tried to control, I think in that case, it was the airflow to the room that we were able to control, or sort of improvements in terms of how long it took compared to the baseline and so on and so forth. We haven't done comparisons at a larger scale. So that was at one conference room. One of the issues is that we don't know if this actually scales very well to larger configurations. So that's a question that remains open. On your second question, the objective of the control is entirely embedded in the MPC formulation that we put in the differentiable layer. And so the objective there is defined as a combination of energy savings and comfort, where comfort we treat as basically deviations from the set point. And so it's trying to do both at the same time, and it has a penalty for that. But we don't have to explicitly define that. We, in the sense that in the forward pass, when the network is already trained, it solves the MPC problem in one go, and it knows what the optimal, quote unquote, set of actions is for solving this MPC problem.
So
a lot of questions.
Yeah, well, it's just Kyle's question, which got a couple of votes here, is it says, fantastic. It seems like this approach could be applied to many energy system applications, but what about riskier applications where the exploration would be potentially dangerous? I don't know if you have any thoughts on that.
Yeah, I mean, this is an open question in general. And what I would recommend in that sense is that you look at the literature that's coming out very recently about providing guarantees in these control scenarios. Right now, that seems to be the biggest bottleneck, that we can't, unlike robust control, where we know how to provide guarantees, we don't know how to do this very well in the context of these black box type models. But there has been some newer work as recent as like a couple of weeks ago that sheds light on how to start doing this. So that's a generic answer, but the more specific answer is like, practically you may want to then do some exploration maybe in some simulation environment or in settings in which you know that there's not going to be any sort of adverse effect, like maybe at night or whatever. Right. So there are other considerations to have there.
Another question, do you have any sense of like how much energy efficiency or cost reduction could be achieved, or have you gotten to that point?
Right, so in the simulation, compared to the baseline controller, we achieved 20%. In the real life test bed, I think the difference was much smaller, about 10 or 12%. But these are numbers that I don't want to use to generalize anything, because every building is going to be different, every situation is going to be different. I would need a lot more data and study to actually give you an answer about that.
Cool. So one question is, you started the presentation asking whether the controller could be replaced by a machine. Yeah. What's your answer?
So I think the quick answer is eventually. So I think right now there's a lot of hesitation to deploy these kind of solutions, even though they are becoming a lot better and faster. And I think the biggest problem is like ensuring that you can provide interpretability and guarantees. This actually provides some interpretability because the model that we learn, the basically simple linear dynamics that we learn, is interpretable. Like you can know what the state is and what the linear combination of the state gives you the next state. So that is interpretable, but still the guarantees of how the control will actually behave are not as strict as the industry practitioners would like them to be.
Right. Well, I found myself like reflecting on the fact that I have like one of these automatic thermostats in my house, but I find myself kind of regularly overriding whatever it's doing. And I was wondering, like, presumably that could be used as some sort of a performance feedback mechanism to further train the algorithm. So you could still use John for a while, or Joe.
Yeah. And in fact, this is an idea that has been on for a great number of years. So I think Mozart is one of the first people to try like reinforcement learning the concept of his house. And this was in the 90s or 80s. Where like every time he switched a light on or off, like that would be a signal for a reward in the reinforcement learning setting. But incorporating that had been hard because of the long training time. But maybe with the new approach, this becomes a lot more practical.
Great. Well, Mario, thank you again for an excellent talk and interesting research.